Okay, so lecture 14 today is about Faraday's law. It's still a continuation of what we have been learning so far because we started by talking about magnetic fields, right? We saw that magnets create magnetic fields. And then if you have a magnet close to another magnet, then or a moving charge in a magnetic field, then they experience a force. We built the discussion up to last lecture where we saw that magnets do create magnetic fields, and so do currents. So an electric current can also produce a magnetic field, and the key concept behind that is that moving charges create magnetic fields, and that's what we've been learning so far. But we can ask ourselves, if a current produces a magnetic field, will the reverse be true? Meaning, can a magnetic field produce an electric current? To answer that question, I have a little demonstration here. This is just, as you can see here, you have copper wires that are coiled close to each other. We learned that that's essentially a solenoid, right? A solenoid is coils of wire that are very closely spaced. This is plugged into the mains. So once I turn this on, current will flow in the coils here, in the coils of wire. We learned last lecture that if you have current flowing through the wire, then there should be magnetic field created through the solenoid. Right-hand rule, point your fingers in the direction of the current flow, and the thumb points in the direction of the magnetic field that's created. We also learned in the last lecture that if you put, for example, an iron, so that's just iron in the core of the solenoid, the function of the iron is to change the permeability mu, and it makes the magnetic field stronger. So this is here to make the magnetic field created by the current in the coil stronger, right? So if it's true that the magnetic field created by the solenoid produces currents, okay? I have here a light bulb and a closed circuit, just coils of wire here that forms the closed circuit here. If it's true that the magnetic field produces an electric current, if I put the bulb in the magnetic field region, then the bulb should light up, right? Because then the magnetic field will create current in here, and current will be dissipated in this resistive bulb. Right, so let's try and see what will happen. Right, turn on coil. All right, you can see there. I hope everyone can see. Start from the top, and as I move down, you can notice an increase in the intensity of the light bulb. And I don't want to bust this bulb, so I'm going to go all the way down. But hopefully you can already see a change in intensity from this height to that height. So of course the magnetic field is in the solenoid, right? You have the most intense magnetic field nearest the source, and the weakest magnetic field farther from the source. So you have weak magnetic field here, and as I move the bulb closer to the solenoid, the magnetic field increases, and therefore the bulb glows brighter. Right. What does that tell us? That tells us that the current created by this magnetic field in the bulb changes. Right. As I move the bulb from top to bottom, the fact that the bulb glows brighter means that the current that's created in this coil increases as the magnetic field increases, moving downwards. Yeah, right. So that is a very good illustration which answers this question, right? So indeed, here a magnetic field can produce a current, okay? Right, and this was discovered by Michael Faraday, and the concept of production of current by a magnetic field is what we call electromagnetic induction. So from the words, you can see here that electricity is induced by a magnetic field. Okay, so electromagnetic induction essentially is what we just observed, that magnetic field creates a current. But there are conditions for which magnetic field can create a current, right? The key idea is that the magnetic flux through a circuit or a loop should change, and the change in the magnetic flux will create an induced voltage or induced EMF, which then creates a current in the loop. Right. Okay, so that's the key idea behind electromagnetic induction. I've underlined the keywords. We will look at each of them in this lecture. So first, you need to have a magnetic flux that is passing through a circuit or a loop. Okay, so let's define what is a magnetic flux. Magnetic flux is essentially the total number of magnetic field lines that's passing through an area. Okay, so we said that we illustrate magnetic fields, we draw magnetic fields using magnetic field lines. So I have here some straws. This will represent my magnetic flux. So if you have magnetic field in a certain area here, in a certain region, essentially if you get an area A, simply count how many magnetic field lines are crossing this area, and that will give you the magnetic flux. Okay, mathematically, you can determine the magnetic flux or the number of magnetic field lines via this equation for any shape of area and for any magnetic field. So it's the integral of B dot dA. So this is a dot product. Right, the dot product can be simplified into a cosine theta function. So this dot product disappears, this dot disappears and becomes a cosine theta, where theta is the angle between the two vectors that are involved in the dot product. So theta is the angle between the magnetic field and the area vector. The area vector is simply a vector that is perpendicular or normal to the surface. So here, if this is the surface that's flat, okay, in the first figure here, the surface is flat, lying down like this. The unit area, the vector area, is just a vector that's perpendicular to that flat surface. So it's a 90-degree vector relative to the surface. Of course, if your surface is oriented this way, then the area vector, normal vector, will be oriented like so, like 90 degrees to the surface. We always take the direction of the normal to be the same as the direction of the magnetic field, so that the cosine will be, well, theta will be 0, cosine 0 will be positive, because we're just counting the number of magnetic field lines. Okay, yeah. So the number of magnetic field lines should be a positive number. Hence, if you are given the scenario where you can define two directions for the normal or the perpendicular vector, because this vector pointing to the left, it's also perpendicular to your area, right? And this vector pointing to the right is also perpendicular to the area. But we will take the vector that is in the same direction as the magnetic field, so that cosine theta will be positive and the total number of magnetic field lines will always be a positive number. Okay, right. So this is the general definition with the integral, but in this course, we will only mostly consider a uniform magnetic field and a flat area A, in which case this integral reduces to BA cosine theta. Right? You'll just have integral of dA, which is A, hence flux is equal to the magnetic field strength times the area, right? It's the cross-sectional area of your surface, times cosine, the angle between the vector that's perpendicular to your surface and the magnetic field. Good. So let's try these two exercises to find the magnetic flux through these two scenarios through these two surfaces. In the first one, you have a ring, and you have magnetic field lines that are pointing into the page. All right, so it's essentially like this. Say you have magnetic field lines and you have the ring in this orientation. All you have to do is find the vector that is perpendicular to your ring, the area through which the flux, the field lines are crossing, right? So you can either, it will be perpendicular to the surface. So we know that the magnetic field lines will therefore be parallel to the normal vector to the surface. So if you then calculate the magnetic flux here, magnetic flux is equal to BA cosine theta. The magnetic field is given 15 milli is times 10 to the minus 3, right? A is the area of the surface. Your surface is circular with a given radius. The area is pi r squared, right, for a circle. So that will be pi times 0.25 squared. And then cosine, the angle will be 0 degrees, right? Because the normal vector, or the vector that's perpendicular to this ring's surface, ring's area, is parallel to the magnetic field lines. So your flux will therefore be, if you plug in all the numbers, you should get what's given as the answer here. Right, in this second scenario, you have the surface that is at an angle theta. Right. The angle that's given is measured relative to the horizontal. Okay. So again, you have flux is equal to BA cosine theta. The magnetic field is given. That's 35 milli. Is times 10 to the minus 3, right? The area, the surface is a square of sides 25 centimeters. So the area is side squared in meters, 0.25 squared. And the angle, right? The angle is not 60 degrees because 60 degrees is the angle between, right? It's like this. Yeah, 60 degrees is the angle between the surface and the horizontal axis. The angle that we are after is the angle between the magnetic field lines and a vector that is perpendicular to the surface. So the angle we're after is actually this angle here. Right? Say your surface is oriented this way, right? The angle we're after is this one, which is 90 minus 60 degrees, or this angle is what we're after. That will be 30 degrees. Good. Right, we're happy with how to calculate magnetic flux, right? So this is how we calculate magnetic flux. Now our definition of electromagnetic induction involves magnetic flux, but electromagnetic induction, meaning magnetic fields creating currents, is formally defined by Faraday's law. So Faraday's law says that the induced voltage, or the voltage that's created in the closed loop, is equal to the negative of the time rate of change of the magnetic flux through the loop. So you have there the magnetic flux being involved. Or if we look at this equation, we can simply say that the voltage, or EMF, so this fancy E, this is the voltage that's created. the voltage that's created is equal to how fast you change the magnetic flux through the loop, right? So if you have a loop and you have magnetic field lines crossing the loop, if you change the number of magnetic field lines crossing a loop, then that creates a voltage in the loop. Right. If you have n loops, then voltage is created through each of the individual loops. Hence, the total voltage that is created is just the number of loops times how fast the flux, magnetic flux, is changed through the loop, right? So you have this dt over dt is the rate of change, right? Whenever we say rate of change, it's how fast something changes. So because you have this d over dt, that tells you that it's how fast the magnetic flux changes that influences how much voltage is created in the loop. Right, so this is a derivative. Okay, the derivative means change. So if you have, you're looking at the changing flux over a finite time interval, then this derivative actually transforms into a delta, which is a change. So delta is the change in flux over change in time. When we say change, this is some final value minus initial value, right? So practically, if you're just looking at a finite time interval, you can calculate how much voltage is created in your loop by determining the final flux in a final number of magnetic field lines crossing your loop minus the initial flux or the initial number of magnetic field lines crossing the loop, divide that by the time interval. Right, so this is how you interpret this equation here. You need to know what's the final number of magnetic field lines crossing your loop minus the initial number of magnetic field lines crossing your loop divided by the time interval over which the change took place. Because you will only have an induced voltage if you have a change in magnetic flux. If the magnetic flux doesn't change, then this numerator is 0 and you don't create any voltage there. Okay. Right, so let's expand this because we already know Faraday's law tells us that the flux needs to change, right, in order to create a voltage in your loop. So flux, we define flux to be equal to B, magnetic field strength, times the area of the surface through which the field lines cross, times cosine theta. So that means that in order to create a voltage, we can change any of these variables here that define the magnetic flux. You can change the magnitude of the magnetic field, right? Just like what I did in this demonstration by moving this wire loop from the top with a low magnetic field strength to the bottom with a higher magnetic field strength. I essentially change how much magnetic field lines are crossing through my loop. And that's why the brightness of the bulb changed, because I changed how much voltage and therefore how much current is created in my wire loop. So that's one way of generating a voltage. Change the magnetic field strength. You can also change the area of the loop, right? Because, for example, you start with a big loop. If you start with a big loop, and the big loop can cover all of this magnetic flux. If you change it with a smaller loop, then maybe there's fewer magnetic field lines crossing that loop. So that's another way of changing the magnetic flux and creating a voltage there. Or you can change the angle between the magnetic field lines, because as we've seen, if you have magnetic field lines crossing perpendicular to your surface, you have maximum flux. But if you orient your surface so that you have, so it's oriented this way, then there are no magnetic field lines crossing your surface. So that's how, changing the orientation essentially changes that angle theta. And finally, because this is a rate of change, right? You can change how much voltage is created by changing how fast you change any of these quantities above, right? So how fast you decrease the area, or how fast you rotate the loop, decreasing the angle, for example. Okay. Just a quick note, right? The voltage, right? The voltage does not depend on the resistance of the loop. Okay. So the idea here is to use Faraday's law, the change in the flux, to determine how much voltage is created. Then once you know how much voltage is created, you can then calculate how much current is created using Ohm's law, right? Ohm's law, V equals IR, right? If you know how much voltage is created in your loop, then you can calculate how much current is created in your loop. Of course, you should know the resistance in your loop, right? So this equation here is from Ohm's law, right? Now the negative sign here is not actually involved in the calculations, but this negative sign has a very important physical meaning. The negative sign tells us the direction for where the current is flowing in the loop, right? And actually, it's such an important concept that it has its own name. It's called the Lenz's law. So Lenz's law just refers to the negative sign in the Faraday's law equation here. Lenz's law gives us the direction for which the induced current is flowing in the loop. Okay, and Lenz's law can become confusing. So let's dissect Lenz's law. It's actually quite a simple principle if we understand the concept of it. Lenz's law says that the direction of the magnetic induction effects is such as to oppose the cause of the effect. Well, that's a big sentence, but what does it actually mean in reality, right? There are two possibilities, right? Either your magnetic flux will increase, or the magnetic flux will decrease. Now let's look at the case where the magnetic flux will increase. So according to Lenz's law, say for example, I have 4 magnetic field lines, okay, crossing this loop, right? Right, the first case is when the magnetic flux increases. Magnetic flux increases means so originally there are 4 magnetic field lines. If I increase that to 6 magnetic field lines, okay, essentially I increase the number of flux crossing this loop. Lenz's law doesn't want this. So Lenz's law always wants to return to the original condition where there was 4 magnetic field lines. So what will happen is that according to Faraday's law, so let's say these blue straws are magnetic field lines that are pointing out of the page, right? So initially there were 4 magnetic field lines pointing out of the page. I increased that to 6 magnetic field lines pointing out of the page. Lenz's law doesn't want this. Lenz's law wants the original 4 magnetic field lines pointing out of the page. What happens is that it creates an induced magnetic field that's pointing in the opposite direction. So these orange straws here, they are magnetic field lines that are pointing into the page. Yeah, they're different colors, meaning they're pointing in opposite directions. So an induced magnetic field is created in the loop, and the purpose of these induced magnetic fields is to cancel out the increase in the magnetic field that happens. Therefore, If these two induced magnetic fields cancels out these two additional magnetic fields, you're then back to the original 4 magnetic field lines. And Lenz's law gives you the direction. So where will these induced magnetic fields come from, right? Where will these orange straws come from? They won't appear out of nowhere. They have to come from somewhere, right? And we learned that magnetic fields are created by currents. That means that a current would have been induced in this loop. The induced current or the current created in this loop then creates these magnetic field lines that cancel out these two additional magnetic field lines, right? So if these magnetic field lines are pointing into the page, use your right hand with your thumb pointing in the direction of the induced magnetic field. The fingers curl in the direction of the induced current. So in this case, right, orange straws mean magnetic field lines into the page, right? Your thumb is pointing into the page, which means that the current is induced clockwise in your wire loop. So the clockwise current in your loop creates these magnetic field lines, which cancels out these two additional lines. So that's for the first case where the flux increases. Did you get the concept of that? Okay, right. So for the second case where the flux decreases, right? So you say you have these 4 magnetic field lines crossing your loop. That's the original number of magnetic field lines. For some reason, for any of the reasons we've listed, like changing magnetic field, changing area, or changing angle, for some reason, for example, from the 4 magnetic field lines, that decreased to 2 magnetic field lines, right? Lenz's law doesn't want that. It wants to have the original 4 magnetic field lines. So what it does, it creates a new magnetic field so that it goes back, the system goes back to the original 4 magnetic field lines, right? So from 4, it became 2. The new magnetic field it creates should then be pointing in the same direction as the original magnetic field, so that then it goes back to these 4 magnetic field lines. Where does these 2 newly created magnetic fields come from? They will come from a current that is induced in the loop. Right? What's the direction of the current? Use the right-hand rule. Okay, this is the created magnetic field. Point your thumb in the direction of the created magnetic field and your fingers curl in the direction of the induced current. So that means that a current that is anti-clockwise is formed in this loop. Okay, the anti-clockwise current then produces these 2 magnetic field lines that brings back the system to the original condition before the flux decrease. That, yeah.
What defines the original 4?
This one. Oh yeah, the original, it could be like, say, for example, I turn this on and you have 4 magnetic field lines represents, for example, 2 milliteslas of magnetic field. So these original magnetic fields that are present, they can come from either a current source or a magnet or a big magnet. It's just magnetic field that's originally present. And that's a very good point, because then we are now talking about 2 magnetic fields, 2 distinct magnetic fields. The first magnetic field is called the external magnetic field. That's the magnetic field that's originally present in the system that's passing through the loop. And then you have the second magnetic field called the induced magnetic field. That's the magnetic field that's created after the change occurred. Okay? So yeah, so those are, we're now talking about 2 distinct magnetic fields. Right? So say you have originally 4 magnetic field lines crossing the loop. This is the external magnetic field. It can come from a magnet or some current source or whatever source, but it's originally present there. if you change these magnetic field lines, right, say from 4 to 2, Lenz's law, we'll want to bring that back to 4 magnetic field lines. It creates a new magnetic field. This is now called the induced magnetic field. The induced magnetic field will oppose the change in the first two.
So, still trying to think of in terms of set up there, is the wire that you bring up to the pole wire.
Yeah.
Would originally have 0 lines through it.
Yeah.
As you pull it through, you're introducing more field lines.
Yeah.
So does Lenz's law want to basically turn that to 0?
0, exactly. So say if I put this down, say let's just assume the magnetic field lines due to the solenoid is pointing upwards. Right? Originally, there's no magnetic field line here. So once I bring it down, Lenz's law wants to oppose the upward magnetic field. So it will create a new magnetic field that's opposite in direction. So that overall it should be 0 magnetic field. So then from there, you can deduce that the current created in this coil is in this direction. Yeah, so right-hand rules, use the right-hand rule to determine where is the direction of the induced current, just like what we were doing there. Okay, so try this exercise out. You have here, so you have here 6, pointing out of the page, these are the blue straws, right? So you have 6 magnetic field lines, and then you have this wire loop. Say, originally you have 6 magnetic field lines here, and then you move the wire loop to the right so that the number of magnetic field lines then decrease. What is the direction of the induced current in this circular loop? Okay, so originally you have here and you're moving this like that. Right, so 6 and then 4. What's the direction of the induced magnetic field once the loop has moved to this position? Yeah, so you have 6 and then became 4. Lenz's law says I want 6 magnetic field lines that are pointing out of the page. Hence, I run out of blue straws. Hence, I have to create 2 more magnetic field lines in the same direction as the original ones, right? So these are the 2 new created magnetic field lines. Your thumb points in the direction of them, and your fingers curl in the direction of the induced current. Yeah. Right, so the magnetic flux is decreasing when you move to the left. Therefore, the induced magnetic field should be in the direction as the original magnetic field, external magnetic field that's originally there, right? Right-hand rule says point your thumb in the direction of the induced magnetic field and your fingers curl in the direction of the current, hence anti-clockwise. Good. All right, try the next one. You have increasing current. And then you have a wire loop above the current. Yeah, it entails 2 steps. So we learned that if you have a current that's flowing to the left, right-hand rule gives you the direction of the magnetic field. So above the current here, you have magnetic field lines that are pointing out of the page. Okay, hence within the loop, you have magnetic field lines that are pointing into the page. Right? And below the current wire, you have magnetic field lines that are pointing out of the page. Right. So it's this scenario here. So you have currents, so orange straws, they're currents that are they're magnetic field lines that are pointing into the page, right? Okay, so say that is the original magnetic field lines that are created by the current in this horizontal wire. The magnetic field lines are pointing into the page, right? You have a circular loop there. Now the current is increasing. Right? So when the current increases, what happens to the magnetic field crossing the loop? The magnetic field should also increase, right? So if your current is increasing in the wire, the magnetic field through the loop will increase. You'll have now more magnetic field lines crossing the loop. So say originally you have 3 magnetic field lines, the current is increasing, hence you have the additional, this is now the new number of magnetic field lines, right? Lenz's law doesn't want this. Lenz's law wants to have the original 3 magnetic field lines. So what does it do? It creates a new magnetic field. Okay. Right, creates a new magnetic field that is then pointing in the opposite direction, right? If the orange straws are pointing into the page, the blue straws are pointing out of the page. So they are directed in opposite directions, the blue and orange straws. So effectively, the created or the induced magnetic field that's pointing out of the page cancels out with the 2 orange straws that's pointing into the page. Okay, if these cancel each other out, then we're back to the original 3 magnetic field lines that are originally present. So what's the direction of the induced magnetic field? It's out of the page, right? These 2 straws will counteract the increase of that magnetic field, and hence the current again is anticlockwise. Okay. Right. So originally, magnetic field lines are into the page. You have these 3 original magnetic field lines. The magnetic flux is increasing because of the increase in currents, right? You have this increase in magnetic flux. Lenz's law doesn't want that, so it will create an opposite magnetic field to cancel out the increase in the magnetic flux, right? And use right-hand rule. Point your thumb in the direction of the induced current and your induced magnetic field, sorry, and then your fingers curl around the induced current. Good. All right. Okay, I hope not too confusing. Just keep in mind there are 2 kinds of magnetic fields there. And we are after the direction of the induced magnetic field because that will give us the direction of the induced current. Okay, so what we've been doing so far is finding the directions. Now here is a numerical example that will help us know how to calculate how much voltage is created. So you have here a circular loop, right, in the plane. So it's like this. Okay, you have orange straws, magnetic field lines pointing into the page, right? The magnetic fields is 0.75 Tesla. And the loop has a diameter initially of 20 centimeters, right? So we're wanting the bigger loop. Okay, we have a bigger loop with a diameter of 20 centimeters, and then the loop is shrinking. So as you can see here, the area of the loop decreases, right? From 20 centimeters, it decreases to 6 centimeters, okay, in 5 seconds. Right? When the loop decreases, the number of field lines crossing the loop also decreases, right? So from, say, example, original 5 magnetic field lines, it decreases to 4 magnetic field lines. and the decrease occurs in 0.5 seconds. What's the direction of the induced current? And then what is the value of the induced current? All right, let's do the direction first. Yeah, so you have the bigger loop, okay, 5 magnetic field lines pointing into the page. You decrease it to 4 magnetic field lines pointing into the page. Lenz's law wants the original 5 magnetic field lines. The induced magnetic field line will therefore point into the page, right? And the induced current should be clockwise. Right, for the voltage, well, we want induced current, okay? The induced current comes from Ohm's law, V is equal to IR, or I is equal to V over R. So that means we need to find what is the voltage V. Okay. So find the voltage V. We know from Faraday's law tells us that the voltage is created by the change in the magnetic flux through the loop. Okay, the negative sign, this is just Lenz's law, which gives you the direction. So when you do the calculation for the voltage, disregard the negative sign, okay? Because as I said, negative sign also only tells us the direction, but the magnitude of the voltage is calculated from the absolute value without the negative sign. So it will be the change in magnetic flux over the time interval for which the change happens. Okay. If we analyze the problem, the change in the magnetic flux is because of the change in the area of the coil, right? Flux is equal to BA cosine theta. So the change in flux can occur by either changing the magnetic field, the area, or the angle theta. In this particular example, it's the area that changed, because area, of course, is equal to pi times the radius squared, and radius is equal to half the diameter. The diameter is what's given. So in this particular example, there is a voltage that is generated because the change in flux is created by the change in area due to the change in the radius of the ring. So it's the change in area that's important. Here, the magnetic field is constant, 0.75 Tesla. Okay, so you have 0.75 Tesla for the magnetic field times the area is pi r squared, but the radius changes. So you have the change in radius there. Or you can always calculate the old area minus the new area. It will still give you, as long as you get the change in area there. Divided by the time interval over which the change happened. Okay, the problem says that the diameter decreases over 0.5 seconds. And that will give you a voltage of 0.04 volts. Which if you use in Ohm's law, so this one is coming from Ohm's law, voltage 0.04 volts divided by the resistance 2.5 ohms should give you the current 1.7 times 10 to the minus 2 amperes. All right, any questions about the solution here? The key there is identifying which among these variables, B, A, or theta changes. And once you identified which variable changes, you can then calculate the change in the flux. All right, so we have now encountered a lot of right-hand rules. So I thought I'd show this table to summarize all the right-hand rules that we've learned and when should we use these right-hand rules. So if you want, you can refer to this table anytime. That's all. These are all the right-hand rules we'll encounter. But so far what we learned is when you have a wire loop and you change the number of magnetic field lines crossing this loop, it will generate a voltage or an EMF and therefore also induce or generate a current. But the loop has a well-defined path, right? It's either the current is going clockwise around the loop or anti-clockwise around the loop. Now the question is, can we also generate a current if we make a metal move in a magnetic field region? So like this scenario here, you have a metal plate that's rotating in this direction as indicated, and the metal plate crosses some region with magnetic field. So say you have a metal plate and you have a magnet at some point there. So here's the magnet representing the magnetic field that's created by the magnet, and the metal plate is rotating. Okay, right. So these here are the segments. We divide the plate into 1, 2, 3 segments for visualization. So notice that as the plate rotates, it will approach this magnetic field region. Right, from a zero magnetic field, it then encounters a magnetic field that's into the page, right? Lenz's law says, therefore, that an induced magnetic field that is out of the page needs to be created in this segment so as to go back to the original no magnetic field through that segment. And therefore, that creates an induced current that's anti-clockwise in direction. Now, when this segment reaches the end of the magnetic field region, it then goes from with magnetic field to without magnetic field. Lenz's law again doesn't want that change, right? So what happens is Lenz's law will induce a magnetic field that's into the page as that segment leaves the magnetic field region. Okay. Right, the induced magnetic field that's into the page then creates an induced current that's clockwise in direction. So what happens is that at that point where you have the magnetic fields, you have these currents, these small currents that are created in that metal region, and we call these eddy currents because they look like eddies or little swirls that you observe in water. Okay, so if you have a current here that's upwards and a current here that's upwards, right, and you have a magnetic field that's into the page, we learned that the metal will experience a magnetic force, and the direction of the magnetic force is from right-hand rule. The current is upwards here, so J hat crossed with the magnetic field minus K hat. This will give you minus I hat. So in essence, there is a magnetic force that is created to the left, and this magnetic force, it's pointing to the left. It will naturally oppose the motion. It opposes the motion of this rotating metal. Okay. And eddy currents are quite interesting. So this is the concept behind it. But this video shows you the application of eddy currents. So hopefully this will work, but maybe I need to switch to as usual here.
At Headrush Technologies, we create innovative equipment for the adventure and amusement market.
Technologies,
we create designed to enhance the
innovative equipment for the
increase participation, and reduce costs. The technology inside many of our devices is eddy current magnetic braking. Eddy currents are forces that occur when non-magnetic metals move through magnetic fields. There is no reaction when the two objects are still, but when motion is introduced, eddy currents are created. These eddy currents oppose the magnetic field, and it's the opposition of these two forces that creates the braking effect. In our devices, when the webbing is pulled out by a participant's weight, centrifugal force sends aluminum rotor arms spinning past stationary magnets within the device. This movement creates the eddy currents within the aluminum arms. The force of these eddy currents oppose the force of the magnetic field, therefore braking and slowing the release of webbing from the device. There are many benefits to eddy current magnetic braking. Low maintenance. Because the braking is magnetic, there are no contacting parts like brake pads that will wear out or fail. That means less maintenance and a low cost of ownership. Self-regulating. The braking resistance automatically adjusts to provide consistent braking across a wide range of participant weights. Children and adults alike will enjoy a similar experience. Smooth and comfortable. Whether jumping, descending, or approaching a platform, the experience is always smooth and easy.
So eddy currents, they are useful, because they create opposing force to the movement of the motion. They are actually quite powerful. They're also used in the braking systems of trains and roller coasters, and even fast speeding things. And eddy currents, they're not only for braking systems, but it's also the principle behind airport security. You know why you have magnetic fields created, and when someone with metal walks through, that creates magnetic currents, which triggers the alarm. It's the same principle in metal detectors. So that ends our lecture for today. We learned that if you have a magnetic field and that magnetic field changes, it creates a current through a loop, which we call the induced current. So we'll look at another example of Faraday's law and electromagnetic induction tomorrow, but have a good day, everyone, and good luck with the test.